Incidentally, if you were looking for the notes from Tuesday, I recorded them, but I forgot to post them. I just posted them last hour. Okay, so here we go, 98. A yo-yo shaped device mounted on a horizontal frictionless axis is used to lift a 30-kilogram box as shown in the figure at the right. So your drawing looks like this. You've got a sort of a small sphere of radius little r, and then the box hangs from that. And then there's a bigger wheel that, and then you pull on it this way with an applied force, which we will call F applied. And we know that this radius here is capital R. Whoa, my board needs to be calibrated. Let's see, so what else do we know? We know that the box has a mass of 30 kilograms. We know that capital R is 0.5 meters and little r is 0.2 meters. The applied force is 140 newtons. Let's see. Let's see. When a constant horizontal force of that magnitude is applied to a rope wrapped around the outside of the device, the box, there we go, has an upward acceleration of 0.8 meters per second squared. Automatically, without doing anything, automatically I'm already thinking about something that I need to do. Right away, what should I do? I just gave you acceleration. Okay. As a general rule of thumb, you guys, these problems are all about forces. If you know the acceleration and you know the mass, find your net force. You're going to need it. Okay? That needs to be like knee-jerk reaction, okay? If you know the acceleration and the mass, find the net force. You're going to need it. All right? Okay, so here's my drawing. Let me smallify this a little bit so we got some room to work. That's right, smallify. Okay, so what are we trying to find? We're trying to find the rotational inertia. So that's the question. That's the question is, what is I? Okay, so let's start with what I just commented on. We can certainly find the net force on the box. So here's what I know. My box is sitting here. It's got a mass of 30 kilograms. I know the acceleration is 0.8 meters a second squared upwards. Therefore, net force is mass times acceleration. That's going to give me 24 newtons, right? Everybody good with that? Okay, well, while I'm thinking about the box, what else do I know about it? What do you got, Alex? Gravity's pulling it down with a force of 30 times 9.8, so negative 294 newtons, right? Negative just to indicate the down. Is that it? Yeah, we ought to be able to find our tension now, right? The tension needs to be big enough so that when I subtract 294, I get 24, right? So what's that give you, 318? Okay, cool. All right. So, yeah, I agree. It looks like we can find the net torque now, right? Because now if I go over here and look at the wheel, I know that I've got my applied force here, which is 140 newtons, and I know I've got tension pulling this thing down with a force of that same number, 318, right?
So that you take the torque and
Yep, torque is a vector, so you can add it just like any other vector. You just got to be careful about your direction, right? Because the applied force is a positive torque, but the tension torque is a negative. Follow? If it's easier, counterclockwise, clockwise, right? So they're working against each other, right? Okay? So, my net torque is going to be, well, let's see, the 140 newtons has a radius of 0.5. That one's going to be the positive one, right? So minus, this is the negative. 318 newtons times 0.2, right? Follow? So what's this going to give us? 70 minus 63.6? Is that right? Get that in my head. Go with that. So that gives us what? 6.4 newton meters. The front? How what?
I don't understand.
I doubled it and then scooted the decimal over. All right. Are we good or no? All right. Are we good? Okay. So great. So we found the net torque. Love it. All right. So the question wanted to know what I was. What's the connection between my net torque and I? Oh, right. Yeah, net torque is I alpha. I like where we're headed with this. All right, so let's see. So net torque is I alpha. So I know my net torque. So to find my I got to figure out alpha. So thoughts about how to find the alpha. It's a one-step thing.
The jumper.
Yep, we're going to use a jumper. Good. So the box has a linear acceleration of 0.8. So I know that A is alpha R. So that means that alpha is A over R, right? So my acceleration is 0.8 meters per second squared. What radius? 0.2, 0.5, something else? 0.3? 0.2. Do we see why? Because the acceleration of the box is the acceleration of the string, right? And the string is a distance of 0.2 meters from the center of the box, of the pulley thingy. Technical term. So what's that give? I can do 4 radians per second squared, right? And we're done. Right? We know our net torque, we know our alpha, so now we can find our I.
Yeah.
Sorry, when I say we're done, we'll be done in one more step. So I is what? Net torque over alpha. So our net torque, what was it? 6.4 newton meters over 4. So that's going to give you what? 1.6 kilogram meters squared.
Wait, so
I'm just confused about that network part of.
Up here,
No, one.
higher up. This guy.
Yeah.
So if you've got a box with 2 forces on it, right? You've got a force that's this way that's whatever, 20 newtons, and a force this way that's 5 newtons. Then to find your net force, you literally just add the 2 forces, right? It'd be 20 plus -5, and you get 15, right? You literally can do the exact same thing with the torque. All right? So, how do I want to do this? So when I found my net torque, what I did was I found the torque provided by this applied force, and then I added the torque provided by the tension. So this 140 times 0.5, this 120 times 0.5 there,
Yeah.
that's the torque provided by the applied force, right?
Yeah.
Well, why didn't I need to worry about the angle here? Why didn't I do sine theta? Because it's perpendicular, right? Your force is perpendicular to your radius. Okay. So does that 140 times 0.5 make sense?
Yeah.
Cool. And then I subtracted the other torque because they're working against each other. Technically speaking, this one's positive because it's counterclockwise, and this one's negative because it's clockwise. Follow?
Yeah.
Does that answer your question?
Yeah.
Are you lying to leave you alone, or you got it?
I just don't get why you didn't use the 24. That's something that force. Not why.
Why didn't you use the? Oh, I gotcha. Oh, I see what you're saying. I see what you're saying. Okay, so for a few reasons. So reason number 1 is the net force on this 24 newtons is the net force on the box. Okay.
Yeah.
The reason I needed the net force on the box was it allowed me to find the tension.
Okay.
Follow?
Yeah.
Even though the box is an integral part of the problem isn't about the box. The problem is about the wheel. So I don't care about the forces on the box, I care about the forces on the wheel. Follow?
Yeah.
Right. Secondly, what is the net force on the wheel? What's the linear acceleration of the wheel? So the linear acceleration of a point here on the wheel is point A, but the acceleration of the wheel as a whole, specifically the acceleration of its center of mass, is 0. Okay? The wheel isn't accelerating, it's staying in one place. Okay? So the net force on the wheel is 0. So if we wanted to, there's a little structure holding this thing up, we could figure out the force that was exerted. Right? Because it would have to be enough to make all your forces cancel out. We can't do it because we don't have the mass of the wheel, but all right. This problem is about not force on the wheel causing the wheel to move, it's about torque on the wheel causing the wheel to rotate. Does that make sense?
Yeah.
Good? Right. Now are you saying good, so I'll leave you alone, or? Okay. Alex, you had a question, I cut you off.
Oh, the angular acceleration, is that of both wheels?
Yeah, the wheels are attached, so they're moving together as one unit.
Okay, okay.
So yeah. Does that make sense?
Yeah.
Okay. Yeah, Alex. Say that again?
Yeah.
Yes. Yeah. Exactly. Yeah. So the reason I hesitated there is technically, you guys, when you talk about the linear acceleration of a wheel, you have to talk about the linear acceleration of a point on the wheel. Do you know what I mean? Because, right, so yeah, so if you, and I knew that was what you were asking, but I just want to make sure you guys understand that technicality. Okay. Good, you guys? This is, like, that's a good problem. Yeah. Could we?
Could we ask because like you have two different masses?
Well, it's changing, right? Because the velocity is changing. So if you specified a moment in time, you know, if you said to me, what's the kinetic energy after 2 seconds? Then 100% we can do that. So we can find the velocity of this thing after 2 seconds. We can find the angular velocity of this thing after 2 seconds. Do you see what I mean? So you can do it, but you'd have to specify a moment in time. And that would have been a good part B to this. All right, was that all of that problem? Was that all we had? I don't mean all we had to do like it was easy, but I mean there wasn't a part B. Okay. All right, real quick while I'm looking at it, because it's the next one on the sheet. Is everybody okay with number 101, the one about the belts? Yeah, because I figured if you got part E right, then you got everything else right. All right, but yeah, so here's the idea with that. Oh. Yeah. Uh-oh, that's a point. Wow, you guys are racking them up this chapter. Between yesterday's cluster. Yeah, that's got to be radians per second. I wrote centimeters per second, but that's wrong. All right. Oh, I wanted that to be different color. All right, so your drawing looks something like this, right?
Yeah.
Okay, so what does it tell you? It tells you that pulley A has a radius of 15 centimeters. Pulley B has a outer radius of 10 centimeters. This inner one here is just 5 centimeters. And pulley C has a radius of 25 centimeters, not drawn to scale. All right. So here's what we know. Pulley A is the drive pulley. In other words, there's some motor or something making pulley A spin. A, B, B prime, C. Okay. So we know that this dude here, the angular velocity of A is 15 radians per second, right? Follow? Right. Now, what is belt 1 sort of doing? Oh, is there a weight somewhere? Oh, is it?
Oh, you just said.
Oh, you're totally right. 10. My bad. Thank you. Thank you. 10 radians per second. Okay. So what is belt number 1 here doing? Spinning with some velocity, right? And therefore making wheel B move, right? Pulley B. So tell me something about the velocities or angular velocities or something of belts or of pulley A and pulley B. Do they have the same angular or same linear velocities? Linear. Because here's why. Imagine, that's okay, that's okay. Imagine a point on this belt. All right? So if that point on this belt moves forward some distance, that means that this point on the belt needs to move forward that same distance. Right? So it's the linear velocities that are the same. Follow? So what I want to do is, I know the angular velocity of A, so let's find the linear velocity of, and this is sloppy notation because what I was just saying to Alex, let's find the linear velocity of a point on the outside of point A, of wheel A. So that's just omega r, right? So it's 10 times 15 gives you 150, what, centimeters per second, right? Does that make sense?
Yeah.
So that must be the velocity of belt number 1. Make sense? That means that's the velocity of a point on the outside of wheel B, too. So that means that the velocity of B is also 150 centimeters a second. Follow? So ultimately, our goal is to figure out what's going on here with belt C. So what's driving belt C, or wheel C? B prime, right? So we got to figure out what's going on with B prime. So tell me, again, some sort of velocity relationship, either linear or angular relationship between the velocity of B and the velocity of B prime. Do they have the same linear or same angular velocity? They always have the same angular velocity, right? Because they're all turning as one uniform wheel, right?
Yeah.
Because they're connected. So I need to find the angular velocity of B. The angular velocity of B should be the velocity of B over the radius of B, right? So that's 150 centimeters a second over 10 centimeters. And so the angular velocity of B is 15 radians per second. Follow?
Yeah.
Why is that important?
That's B prime.
Because that's also the angular velocity of B prime. Now we can find the velocity of B prime, which is the velocity of the belt, which is the velocity of C. Follow?
Yeah.
All right, so let's see. So let's finish this up. So the velocity of B prime should be the omega of B prime times the radius of B prime. So that's 15 radians a second times 5 centimeters. So that's going to give me, what, 75 centimeters a second? Follow? Sorry, my board work is really crappy here. Everybody okay? All right, so that means then that the velocity of C at the outside is 75 centimeters a second. So now I can find my omega. Omega of C is the velocity of C over the radius of C. So 75 centimeters a second over 25 centimeters does in fact give you 3 radians per second, not centimeters per second. That's the point. Ask me a question.
Okay, is it purely coincidental that on your proportion of radius of A and B
Corresponds to the ratios of their angular velocities. I do not believe that is coincidental. Although they're inverses, I believe, aren't they?
yeah, they're inverses?
Yeah. No, that's not coincidence. I would be hesitant to.
I feel like it's okay.
I'm worried that if you had one more pulley in here, that might mess things up.
What are we just sticking with you?
No, I guess you're right. I guess that should hold. Well, no, I think every time
Let's just make it
here smaller radius was bigger angular velocity. Here bigger radius was smaller angular velocity. No, I think I would be really careful with that. I think that if this smaller wheel had been bigger, that would change that result. I think whether it is inverse or direct proportion. I don't know. I'd have to monkey around with it. I don't want to do it right now, but.
if it's just two wheels and one square.
Right.
That would be okay. That's,
Oh, I got you. I see what you're saying. Yeah. Yes.
that would be,
Right. Yes. For one belt. Yes, I agree.
yeah.
Okay. What else do we need to talk about? Yeah. 62.
For some reason,
You kept getting what?
I'm getting the answer.
Hmm.
Then you do one third, then rod
That's MR squared.
That's exactly correct. Yeah. So you find mr squared for the first dot, or for the first ball, mr squared for the second ball, mr squared for the third ball, and just add them up. Because it says they've been glued to a rod of length, blah, 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 and negligible mass. So the rod itself doesn't have mass. If it did have mass, then you do 1/3 ml squared for that, or, yeah, and then add it to the others.
to the others without.
Right. Does that make sense, Ethan? Yeah.
Could you please do D for the same problem?
From 62? Oh, okay. So we're trying to find the slope of the kinetic energy versus the rotation rate. Oh, yeah. So in blah, blah, blah. Let's try this again. So we want a graph of kinetic energy versus the square of its rotation rate. So rotational kinetic energy is going to go on this graph. Angular velocity squared is going to go on this axis. And it says, what's the slope of the line? Well, the equation for rotational kinetic energy is 1/2 I times omega squared. So if I gave you a graph that looked like this, y equals kx, what's the slope of that line? K. So here, instead of y, we've got RKE, and instead of x, we've got omega squared. So the slope must be 1/2 of I. Does that make sense? So that's all there is. I don't mean that to sound like it's not trivial, but I mean that's how you do that.
Can you just do all of
Do all of 60, sure. Okay. All right, is everybody okay with D now that we've done D? Okay. Let me do this. Let me do 62B. And if you can do B, A, and C are more of the same.
Yeah.
Fair?
Yes.
Okay. So, in order to do 62, we got to find the work. And the problem doesn't give us any information about forces or torques. So my knee-jerk reaction when I see work is I think, oh, well, I'm going to do force times distance, or I'm going to do torque times change in theta. But that doesn't help me at all here. Okay? So the only way we can find the work is to use the work kinetic energy theorem. Oh, that was not what I wanted to happen. All right, so in this problem, our work should equal our change in kinetic energy, right? Specifically rotational kinetic energy, I guess, I'm being sloppy about my notation. So what I need to do is, for part B, I need to figure out what the kinetic energy is when it's spinning at 20 radians a second, find the kinetic energy when it's spinning at 40 radians a second, and then just subtract them. Okay?
Yeah.
So to do that, we got to find our I. So I, for our object, is the sum of all of the particles' mass times their radius squared. So there are 3 particles, because the rod itself is massless. So it looks to me like that first particle is going to be m times d squared, right? The second particle is m times, what's r for that second particle? 2d, right? And then for the third one, it's 3d, right? Follow?
Yeah.
So 2d squared is actually 4d squared, right?
Yeah.
And this is 9d squared, so I've got 9 plus 4 plus 1, so that's 14d squared. So I've got 14 mv squared is I. Follow? Did I do that too quick with the 14?
This is the length of L, like the entire thing, so wouldn't D just be 1/3 of it? So it'd be 1.
Yeah, well, I mean, yeah, so D is, I was just going to use D as 2 centimeters. But yes, what you're saying, yes, 100%. Okay. All right, so yeah, now we actually need some numbers here. So it gives us the mass of each of the particles, and then, like Jack was just saying, it tells us L is 6 centimeters, so the D is 2 centimeters. So this becomes 14 times 0.01 kilograms times, who wrote this problem? 3 centimeters, so 0.02 meters squared, right? Follow?
Okay, is that for only particles?
Nope, that's for all of them, because we totaled them up. You see that? So the 14 accounts for the fact that
Yes.
some of the masses are counted more than once. All right, so I don't know, let's give you some number. Whatever, you guys can figure out what that number is, right? You good up to there?
Yeah.
All right, and then, whoa, weird. So then, just find your change in kinetic energy. So for part B, here's what I know. I know that my initial angular velocity was 20 radians per second, and my final angular velocity is 40 radians per second. So part B says how much work is required. So my kinetic energy initially is 1/2 times that I times my initial angular velocity squared. And then the final, you use the final, and then you just subtract.
And like kind of on topic, kind of same. For those 3 particles, the angular velocity would be the same. Would be different. Like how would they compare that angular velocity?
So imagine that the 3 particles are on this meter stick, right? Which way is the drawing? Right, so, right? They're all moving as a unified front, right? So if I rotate from here to here, all 3 particles rotated through 90 degrees in the same time. So they all have the same angular velocity, but the one at the outer edge moved a bigger distance in that same time, so it has a bigger linear velocity. It's the same rationale for the pulleys when I was here. That's why these, both the big B and the little b, had the same angular velocity, but different linear velocities. Does that help? Yeah. Good. Right. What else, you guys? $66? Oh, good. Yes, 100%. Cool. All right, here we go, 66. So I'm going to make a really crappy version of the drawing here. We got this sphere mounted, and then a pulley, and then a box. All right, so there's our drawing. All right, so this guy has a mass of capital N and a radius of capital R. This guy has a rotational inertia of I and a radius of little r. And this dude has a mass of little m. Ugh. Can you guys tell that's capital M? I'll try to be more careful in the future. All right, so here's what we know. We know that capital M is 4.5 kilograms. We know that it is a spherical shell, which is important because it tells me that I is 2/3 or 2/5. Good, 2/3 because it's the bigger rotational inertia, right? Let's see, what else? Oh, well, that was generic now, to be honest. So, but yeah, I'll be more careful about it. So you're right, it should be capital M times capital R squared, where capital R is 8.5 centimeters or 0.085 meters. All right, so I can use that to find I. Cool, so we'll do that in a minute. Let's see, what else? A massless quark, hooray, passes around the equator of the shell over a pulley of rotational inertia. So I, over here, is 3 times 10 to the negative third. Oh no, my board is going. We're going to meter squared. and the radius little r of 5 centimeters, so 0.05 meters. And it's attached to a small object, m. The little m is 0.6 kilograms. There's no friction on the pulley's axle. The cord does not slip on the pulley. That's important, right? So that means that the velocity of my rope is the same everywhere, right? What is the speed of the object when it has fallen 82 centimeters after being released from rest? So this thing is going to go down 0.82 meters. Oh, my finger didn't listen to me. 0.82 meters. And we had an initial velocity of 0. Cool? All right. Now we can start. I know, right? Yeah. I know, these problems are involved. All right. Thoughts about where to start? Sure. Find the total rotation. When you say total rotational inertia.
Pulley and the sphere.
Oh. Does that work? I guess so. I didn't think to do it that way. That might be a better way than what I did. I guess I should distinguish between these two eyes. That's I for the pulley. Let's call this IS as an eye of the sphere, which is not the same. Never mind, I won't make that joke. All right. All right. What number are we on? 66. You could use a bad joke. I was going to say it's not the same as eye of the tiger. That's why I didn't say it. All right. 0.021675 kilogram meters squared is that. Let's see. Did you do it that way, Kurt, where you just added the two inertias?
I did earlier problems in the last section like that.
I don't know why I'm apprehensive about that. Say that again?
I skipped this problem because I looked at it, but now looking at it, that's the way I would do it. So I tried to make earlier problems in it.
Can it work? The reason I'm hesitating is because let me not do it, and then at the end, let's see if it would have worked, because I'm apprehensive about it. All right, but I agree that we absolutely need these two rotational inertias, and then let's see if adding them together would have worked. All right, so we got that. What else, guys? We got to use that 82 centimeters somehow. What's the 82 centimeters there for?
Gravitational.
Yeah, let's find the change in gravitational potential energy, right? Okay, so so our change in U, gravitational, should be the mass of the sphere, which is 0.6 kilograms, times the acceleration of gravity, which is 9.8 meters a second squared, times the distance it went down, which is 0.82 meters. And so you get, I guess I should put a negative in here because we're losing that energy, right? So that gives you negative 4.8216. I'm being really keeping all my significant digits. All right, so that means that our change in, oh, you guys tell me, what does that mean? Well, but it's not just rotational. Kinetic, right? So that means that our total gain in kinetic energy is positive 4.8216 joules. So specifically, that's the kinetic energy rotational of the sphere plus the kinetic energy rotational of the pulley plus the kinetic energy regular style of the stupid little mass thing. I don't know why it's stupid, but it is. Sorry, little mass. All right. Hello? Okay. So, yeah, so here's why I hesitated. They have different angular velocities, right, because they have different radii. So, yeah, I think that's going to mess us up. I think we do have to keep them separate. Okay, so is everybody good up to here? All right, so let's see. So this is the kinetic energy of this guy is 1/2 of this I, 0.021675, times its angular velocity squared, plus this guy is 1/2 of its I, which is 3 times 10 to the negative third, times its angular velocity squared, plus 1/2 of this mass, which is 0.6 kilograms, times its velocity squared. All right, so we got a big long equation, right? With two variables, velocity and angular velocity, right?
Is the linear velocity for all of the things the same? It's all the same thing.
Very good.
So can you convert all the W's into these?
Exactly. That's exactly what you got to do. And I realize even these omegas aren't the same, right? So I probably should have put omega for the sphere and omega for the pulley. But you're exactly right. Each of those omegas is the velocity of the rope divided by the radius of the thing the rope goes around. Follow? So, and then from there, I mean, you're 90% done now. So this becomes this times velocity over the radius of the sphere, which is 0.085 squared, right? Plus this mass times velocity over velocity of the pulley is 0.5 rather, squared, plus 1/2 times 0.6 times v squared. So now our only unknown is the velocity, so we can do some algebra solve for that missing velocity. So let me pause there for a minute. Does that all make sense or no? And Kurt, do you see what the issue is now? Perfect. So if you find that velocity, you end up getting, here's what I end up with, 4.8216 joules equals, this whole mess, when you simplify it all out, gives you 2.4 v squared. And if you solve for v, you get 1.42 meters a second. Which I think was what the question was asking for?
Yeah.
Correct. Yeah, right, I know, right? All right, good? Okay. All right, we got about 5 minutes. Was there anything on the multiple choicey stuff from yesterday that didn't get resolved? I understand it was late, but was it helpful?
Yeah.
Okay, all right. My goal is to get you those at the start of next chapter, all right? And just hopefully I won't fall behind for the following chapter. All right, so here's the deal. I'm only around for about 20 minutes after school today. I have a 3:30 dentist appointment, which I didn't realize yesterday. But I'm around in the morning. So if you have last minute questions, let me know. If you're not going to be here for one reason or other, shoot me an email so that I know what's going on with you. Go. So that is that. Oh, one other quick thing. So I'm going to do something tomorrow that I haven't done before. I was writing the test. There were a couple problems. I was like, God, this is such a good problem. I really want to put on the test. But I was worried A, about the length of the test, and B, about the difficulty of the problem. So there are a couple problems that I think are really good problems that I want to do, but I thought they were too tough or would make the test too long. So I'm going to give you 3 problems to work on over the weekend. Okay? So when you're done with the test, I'm going to have you pick up 3 problems, do those over the weekend, and we'll go over them on Monday. Sorry? They're multiple choice, but they're free response length. You know what I mean? You know how some of those multiple choice questions are too long to be multiple choice? Yeah. So, but I figured the fact that they're multiple choice might help you kind of zero in on if you're doing it right or not. So. All right, guys.